You know the word empty. You understand what it means when a room is empty, or a street or a stretch of desert highway at night. Empty means the absence of something that could be there. It means space waiting to be filled. But when we talk about cosmic voids, the vast regions between galaxies where almost nothing exists, we're not talking about empty rooms or empty highways. We are talking about emptiness on a scale that makes those comparisons meaningless. These voids are not small gaps between stars. They are not the spaces you see when you look up at the night sky and notice darkness between points of light. They are regions so large that entire galactic superclusters could fit inside them. They are volumes of space where, if you were somehow placed in the centre, you could look in every direction and see nothing but darkness for distances that light itself takes hundreds of millions of years to cross. And they are not rare. They are not anomalies. They make up most of the universe. When astronomers first began mapping the universe beyond our own galactic neighbourhood, they expected to find galaxies distributed more or less evenly, scattered across space like stars scattered across the night sky. What they found instead was structure. Galaxies clustered together in groups and superclusters, yes, but more importantly, they avoided certain regions entirely. There were vast stretches of space where galaxies simply did not exist. These were the voids, and the more we mapped, the larger and more numerous they became. The word void sounds dramatic, like something from science fiction, but it is the most accurate term we have. These are not regions where matter is merely sparse. They are regions where the density of galaxies drops to nearly zero. A typical void might contain 1/10 the number of galaxies you would expect to find in an equivalent volume of space elsewhere in the universe. Some contain even fewer, and the largest voids, the supervoids, are so immense that they challenge our ability to comprehend distance itself. This is not a story about what fills the universe. It is a story about what doesn't. It is about the architecture of absence, and how that absence defines everything else. Because the voids are not empty space waiting to be filled. They are the default state of the universe. The galaxies, the stars, the clusters and filaments we think of as the universe, those are the exceptions. We live inside an exception, surrounded by exceptions, and so we mistake the exception for the rule. Understanding the true scale of voids means understanding that most of the universe is not like the region we inhabit. It means recognizing that the cosmos is not a vast ocean dotted with islands of matter, but rather a thin web of matter stretched across an ocean of emptiness. And it means confronting the fact that this emptiness is not a flaw or a gap in creation. It is the structure itself. When you stand outside on a clear night far from city lights, you see thousands of stars. They appear scattered across the sky, some clustered in the bright band of the Milky Way, others isolated in the darker regions between constellations. The distribution feels random at first glance, but if you study the sky long enough, patterns emerge. The stars are not evenly spread. Some regions are dense with light. Others are conspicuously dark. This is your first encounter with cosmic structure, though you are seeing only the nearest layer of it. Now imagine you could somehow step outside our galaxy entirely and look back at the local universe from a distance of several million light years. You would see the Milky Way as a single point of light among many others. Our galaxy belongs to a small collection called the Local Group, which includes Andromeda, Triangulum, and several dozen smaller dwarf galaxies. From this vantage point, the Local Group would appear as a modest cluster, nothing remarkable, surrounded by other similar clusters scattered through space at various distances. If you continued moving outward, pulling back your perspective to encompass tens of millions of light years, you would begin to notice something unsettling. The galaxies are not distributed evenly. They gather along filaments and sheets, like cities connected by highways, leaving vast regions in between where almost nothing exists. These dark regions are not obscured by dust or hidden behind brighter objects. They're genuinely empty. No galaxies, no galaxy clusters, just space extending in all directions for distances that dwarf the space between individual galaxies within a cluster. This is where our intuition about neighbourhoods begins to fail. On Earth, if you live in a rural area, your nearest neighbour might be a mile away, or 5 miles, or even 10. But there are still neighbours. The distribution might be sparse, but it is relatively continuous. You could walk in any direction, and eventually encounter another house, another town, another centre of activity. The cosmic voids are not like this. They are regions where you could travel in a straight line for 100 million light years and encounter fewer galaxies than you would find in a single rich cluster occupying a space just a few million light years across. The comparison to human neighbourhoods breaks down completely when you consider what this actually means in terms of isolation. If you lived in a house where your nearest neighbour was proportionally as far away as galaxies are separated in a void, that neighbour would not be in the next town or even the next state. They would be on another planet, another star system. The loneliness of void galaxies is not something we have an earthly equivalent for. It exceeds our normal experience of distance and separation by factors that make the comparison itself almost meaningless. Astronomers first noticed these missing neighbours in the 1970s and early 1980s, when galaxy surveys became detailed enough to map three-dimensional positions rather than just angular locations on the sky. Before this, galaxies had been catalogued primarily by their positions as seen from Earth, which compressed all distance information into a flat projection. It was like looking at a city from directly above and trying to understand its layout without knowing which buildings were close and which were far. When redshift measurements allowed astronomers to determine distances, the true structure emerged. Galaxies were not scattered randomly through space. They formed walls, filaments, and clusters, all surrounding enormous regions where galaxies were conspicuously absent. The first major void discovered was in the constellation Boötes. Astronomers conducting a survey of galaxy redshifts noticed a region of sky where galaxies suddenly became extremely rare. As they mapped more of this region, they realized they were looking at a spherical volume of space roughly 300 million light-years across, containing almost no galaxies at all. This was not a small gap between clusters. This was a hole in the universe's structure large enough to contain thousands of galaxies if they had been distributed at average cosmic density, but which instead contained perhaps a few dozen at most. To understand how striking this discovery was, consider what astronomers expected to find. The prevailing assumption was that the universe, when viewed at large enough scales, would appear relatively smooth and uniform. Yes, galaxies clustered together locally, but these clusters were thought to be relatively isolated features scattered throughout space with no particular organisation. The Boötes void contradicted this assumption fundamentally. It suggested that the universe had structure at scales far larger than anyone had anticipated. It meant that clustering was not just a local phenomenon. The organisation extended across hundreds of millions of light years, and the most prominent feature of that organisation was not the presence of matter but its absence. The Boötes void was not unique. As surveys expanded and deepened, more voids appeared. They were everywhere. The universe began to look less like a roughly uniform distribution of galaxies and more like a sponge, with matter concentrated along the thin walls and filaments, while the bulk of the volume remained empty. This sponge-like structure, often called the cosmic web, is now understood to be the fundamental architecture of the universe at large scales. The galaxies we see, the clusters and superclusters we map, are not the primary feature. They are the edges, the boundaries, the thin surfaces surrounding emptiness. What makes this distribution so strange is that it violates our intuitive sense of how things spread out. If you pour sand onto a table, it spreads relatively evenly. If you release gas into a room, it diffuses uniformly. Even if you drop objects randomly from above, they will scatter with some degree of regularity. But the universe does not behave this way. Gravity pulls matter together into filaments and nodes, and in doing so, it empties the regions in between far more thoroughly than random distribution ever could. The voids are not accidents. They are the inevitable consequence of how gravity shapes structure over cosmic time. The process began in the early universe, when matter was distributed almost uniformly but not perfectly so. There were tiny fluctuations in density, variations of less than 1 part in 100,000. These fluctuations were the seeds of all structure. In regions that were slightly denser than average, gravity pulled in more matter from the surroundings. In regions that were slightly less dense, matter was pulled away toward the denser areas. Over millions and then billions of years, this process amplified. The dense regions became denser, the sparse regions became sparser. What began as tiny ripples in an otherwise smooth distribution became the vast cosmic web we observe today. When we say a region is empty, we mean it contains far fewer galaxies than the cosmic average, but far fewer is an understatement. In a typical void, the galaxy density drops to 10% or less of the average. In some voids, it drops to 1%. You could place our entire local group, the Milky Way, Andromeda, and all their satellites, inside a void, and it would be one of the only structures visible for 100 million light-years in any direction. If human civilization had evolved in a galaxy located inside a large void, our understanding of the universe would have developed very differently. We would have looked out and seen almost nothing. The nearest galaxies would have been so distant that early telescopes might not have resolved them at all. We would have lived in an island universe, alone in an ocean of darkness, with no clear evidence that anything else existed beyond our own galaxy, until our technology became sophisticated enough to detect the faintest, most distant points of light. This is not hypothetical. There are galaxies inside voids. They are rare, but they exist. These void galaxies are among the most isolated objects in the universe. They did not form in the dense environments where most galaxies condense from the cosmic web. They formed in regions where matter was already sparse, and as the universe evolved, the expansion of space and the gravitational pull of surrounding filaments made those regions even more empty. A galaxy in the centre of a large void is separated from its nearest galactic neighbour by distances far greater than the distance between the Milky Way and Andromeda. And unlike our galaxy, which is part of a group that will eventually merge into a single large galaxy, void galaxies will likely remain isolated for the rest of cosmic time. The isolation of these galaxies is not just spatial, it is also temporal and evolutionary. Galaxies in dense environments interact with their neighbours. They collide and merge, they exchange gas, they trigger bursts of star formation through gravitational interactions. This activity shapes their structure and determines their evolution over billions of years. Void galaxies experience almost none of this. They evolve in silence, undisturbed by neighbours, slowly consuming their gas and forming stars at a leisurely pace until their reserves are exhausted. They are the hermits of the cosmic web, and their isolation has made them fundamentally different from galaxies like our own. The missing neighbours are not missing because they were destroyed, or because they never formed in those regions due to some local condition. They are missing because the initial distribution of matter in the early universe was not perfectly uniform. There were slight variations in density, regions where matter was marginally more or less concentrated. Over billions of years, gravity amplified these variations. Denser regions attracted more matter and became denser still. Less dense regions lost matter to their surroundings and became emptier. The process was gradual, but relentless. The voids grew as the filaments grew. The structure we see today is the mature result of that process, and it is still continuing. What we are seeing when we map the cosmic web is not a snapshot of a static structure. It is a moment in an ongoing process of separation. The voids are expanding, the filaments are thinning, and as the universe continues to age, this separation will become more extreme. The regions where galaxies cluster will remain gravitationally bound, held together against the expansion of space. But the voids will grow larger. The distances between void galaxies and their nearest neighbours will increase. The universe will become more empty, not less, as time goes forward. This means the missing neighbours will become even more missing in the future. What we observe now is actually a relatively clustered state compared to what will exist billions of years from now. We are living in an era when the cosmic web is still visible, when galaxies are still close enough to interact and merge, when the night sky of a typical galaxy is still populated with visible neighbours. In the far future, this will not be true. Galaxies will recede from each other. Voids will dominate more and more of the universe's volume, and the typical galaxy will find itself in ever greater isolation, surrounded by emptiness that deepens with every passing billion years. There is a thought experiment that helps clarify what cosmic voids actually are. Imagine you are placed at the exact centre of a large void, suspended in space with no galaxy visible in any direction. You have a spacecraft capable of travelling at any speed you choose, and your goal is simple: reach the nearest galaxy. The question is not whether you will succeed. The question is how long it will take, and what that duration reveals about the nature of emptiness at cosmic scale. If you chose to travel at the speed of a commercial airliner, roughly 500 miles per hour, you would never reach the nearest galaxy within any time frame that has meaning. The universe itself would age and die long before you covered even a tiny fraction of the distance. This comparison is almost too absurd to be useful, but it establishes a baseline. Human speeds, even our fastest machines, are completely irrelevant at these distances. They do not merely fail to be sufficient, they fail to register as motion at all on the scale required. So you increase your speed, you accelerate to the velocity of Voyager 1, the fastest human-made object to leave our solar system, currently travelling at roughly 38,000 miles per hour relative to the Sun. This is fast by any earthly standard. At this speed, you could circle the Earth in about an hour. You could reach the Moon in less than 7 hours. You could travel from the Sun to Earth in just over 100 days. But to cross a typical void at this speed would take billions of years. Not millions, billions! The Voyager probes, launched in 1977, have travelled for nearly 50 years and have barely left the immediate neighbourhood of our solar system. They are still well within the influence of the Sun's gravity. They have not even reached the nearest star, and they never will within any human conception of time. The distances involved do not respond to these speeds. They do not acknowledge human effort or engineering. A void is not something you can cross with persistence or patience. It is something that requires an entirely different framework for understanding motion and time. You decide to travel at the speed of light. This is the fastest anything can move through space according to the laws of physics as we understand them. Light crosses the distance from the Sun to Earth in roughly 8 minutes. It travels from the Sun to Pluto in about 5.5 hours. It crosses the diameter of our solar system in less than a day. At this speed, human-scale distances collapse into irrelevance. The entire solar system becomes a traversable space measured in hours. But even at the speed of light, crossing a void takes a very long time. A small void, perhaps 50 million light-years across, would take 50 million years to traverse at light speed. A typical void, closer to 100 million light-years in diameter, would require 100 million years. And the largest voids, the supervoids we will discuss later, can be 300 million light-years across or more. To cross one of these at light speed would take longer than the entire history of complex life on Earth. Longer than the time since the dinosaurs first appeared. Longer than the time since the first vertebrates crawled onto land. You would begin your journey at the speed of light, and you would still be travelling in darkness, with no galaxies visible in any direction, for a duration that exceeds the span of entire evolutionary epochs. This is where our intuition fails completely. We understand that space is large, but we think of largeness as something that can be overcome with sufficient speed. If something is far away, you simply move faster, but the voids are so large that even the maximum possible speed is not enough to make the crossing feel brief. Light itself, which crosses interplanetary distances in minutes and interstellar distances in years, requires hundreds of millions of years to cross these empty regions. And during that entire journey, you would see nothing. No stars, no nebulae, no distant glimmers of galaxies, just absolute darkness in every direction. It is difficult to convey what this darkness would actually mean. On Earth, even in the most remote deserts or the open ocean far from land, you are never truly isolated from reference points. During the day, the sun provides orientation. At night, stars fill the sky. You can navigate. You can measure your position relative to something. But in the centre of a void, travelling at light speed toward the nearest galaxy, you would have no reference points at all. The galaxies behind you would have receded beyond visibility. The galaxies ahead would not yet be visible. You would exist in a featureless black sphere, unable to determine whether you were moving or stationary, unable to see any change in your surroundings for millions of years at a time. The duration of such a crossing is not abstract. It has real implications for what the void actually is. When we say a region is empty, we do not just mean it lacks matter. We mean it is separated from matter by distances so great that even light, the fastest possible messenger, requires geological spans of time to traverse them. This is not emptiness in the sense of an empty room. It is emptiness in the sense of a separation so profound that it severs any possible connection. A galaxy in the centre of a void is not merely distant from other galaxies. It is isolated in a way that makes interaction impossible. No signal can cross the void quickly. No event on one side can influence the other side in any immediate sense. The void is a barrier not made of matter but of sheer distance. And this is just for typical voids. When we discuss supervoids, the distances multiply. The largest known void, the KBC void, may be as much as 2 billion light-years across. If you were placed at the centre of this structure and began travelling at the speed of light toward the nearest dense region of galaxies, you would be travelling for 2 billion years. That is roughly half the age of the Earth. It is longer than the time since the first multicellular organisms appeared in the fossil record. You would cross this distance and arrive at a universe that had aged significantly during your journey. Galaxies would have evolved. Stars would have lived and died. The cosmic background radiation would have cooled measurably. The void would have expanded slightly due to the acceleration of cosmic expansion. You would arrive not just in a different place, but in a different era. This reveals something fundamental about what voids are. They are not just regions where galaxies happen to be missing. They are regions where distance itself becomes a dominant feature of reality. In a dense galaxy cluster, distances between galaxies are small enough that interactions happen frequently. Galaxies collide and merge. They exchange gas and trigger star formation in each other. They're gravitationally bound into a single evolving system. But in a void, distance prevents all of this. The galaxies are so far apart that they might as well exist in separate universes. They do not interact. They do not influence each other. They evolve in isolation, shaped only by their own internal processes and the gradual expansion of space around them. The desert crossing thought experiment also reveals the relationship between distance and time at cosmic scales. On Earth, we think of distance as something spatial and time as something separate. You can travel a certain distance in a certain amount of time, and these are independent variables. But in cosmology, distance and time become inseparable. The distance across a void is so large that it must be expressed in units of time. We do not say a void is a certain number of miles or kilometers across, because those numbers are too large to be meaningful. We say it is a certain number of light years across, which is a measure of how long light takes to cross it. Distance becomes duration, space becomes time, and the void becomes not just a region of space but a span of time, a duration you would have to endure to cross it, a temporal barrier as much as a spatial one. Even more striking is what this means for the history of light itself. Photons that left a galaxy on one side of a void hundreds of millions of years ago are only now arriving at galaxies on the other side. The light we see from distant galaxies has been travelling through voids for most of cosmic history. It has crossed unimaginable distances through absolute darkness, carrying information about galaxies as they were in the distant past. When we observe a galaxy on the far side of a void, we are not seeing it as it is now. We are seeing it as it was when the light left, which may have been before complex life existed on Earth. The void itself becomes a kind of time machine, preserving ancient light and delivering it to us across durations that exceed human comprehension. This is the true nature of the desert crossing. It is not a journey you could survive or complete. It is not even a journey in the conventional sense. It is a measure of separation so extreme that it redefines what we mean by distance, isolation, and the structure of space itself. The voids are deserts not because they are barren, though they are. They are deserts because crossing them requires durations of time so vast that they become indistinguishable from eternity. And yet they are real. They exist, and they make up most of the universe's volume. There is a peculiar challenge in astronomy that does not exist in most other sciences. Astronomers must name things that are defined by absence rather than presence. A mountain has a clear existence. You can point to it, measure its height, describe its composition. But how do you name something that is not there? How do you catalogue a region characterized entirely by what it lacks? This is the problem astronomers faced when they first began to recognize the empty regions between galaxy clusters. They needed a word, a term that would allow them to discuss these regions systematically, to compare them, to study their properties as if they were objects in their own right. The word they chose was void. It is a simple term, almost poetic in its starkness. A void is an emptiness, a gap, an absence of substance. In everyday language, it carries connotations of loss or incompleteness, as if something that should be present has been removed. But in astronomy, the term is more neutral. It does not imply that anything is missing in the sense of being lost. It simply describes a region where galaxies are far less numerous than the cosmic average. The void is not a hole torn in the fabric of the universe. It is a natural feature of cosmic structure, as fundamental as the filaments and clusters where galaxies concentrate. Before the term void was adopted, astronomers had no good way to talk about these regions. They could describe them as underdense areas, or regions of low galaxy density, but these phrases were cumbersome and did not capture the striking nature of what was being observed. The voids were not just slightly less dense than average, they were dramatically, conspicuously empty. A void is not a region where you find fewer galaxies. It is a region where you find almost no galaxies at all. The difference between a void and an average region of space is not subtle. It is stark, and so a stark term was needed. The choice of the word void reflects an important conceptual shift in how astronomers understood the universe. Before the discovery of large-scale structure in the 1970s and 1980s, the prevailing view was that galaxies were distributed more or less uniformly when averaged over large scales. Yes, there were clusters and groups where galaxies gathered more densely, but these were thought to be local concentrations within an otherwise smooth distribution. The space between clusters was not considered particularly important. It was just space, the neutral background against which galaxies and clusters existed. But when detailed surveys revealed the true extent of the voids, this view became untenable. The universe was not a smooth distribution with occasional clusters. It was a network of filaments and walls surrounding vast empty regions. The voids were not incidental gaps between clusters. They were enormous structures in their own right, comparable in size to the largest concentrations of galaxies. In fact, the voids were often larger than the clusters. A typical rich galaxy cluster might be 10 or 20 million light-years across. A typical void could be 100 million light-years across or more. The voids were not the spaces between the important structures. They were the dominant structures. This realization forced astronomers to acknowledge that the voids needed to be studied as objects, not just as absences. And to study something, you must be able to name it, classify it, and measure its properties. Hence the term void entered the astronomical lexicon as a technical designation. A void is now defined as a region where the density of galaxies is significantly below the cosmic mean, typically less than 10% of average density. Voids have boundaries, though these boundaries are not sharp. They have sizes which can be measured. They have shapes, which range from roughly spherical to highly elongated. They even have internal structure in some cases, with smaller voids nested inside larger ones or filaments of galaxies threading through their interiors. The naming of voids also revealed something about human expectations. We name things we consider significant. Mountains, rivers, cities, stars, all receive names because they matter to us, because they are landmarks in our physical or conceptual landscape. The fact that astronomers felt compelled to name the voids suggests that these regions, despite being empty, are significant in their own right. They are not voids in the sense of being negligible or unimportant. They are voids in the sense of being vast, coherent, and essential to understanding the structure of the universe. But naming the voids also raised new questions. If these regions are so empty, what happened to the matter that should have been there? The universe began in a state that was almost perfectly uniform. Matter was distributed nearly evenly across all of space, with only tiny fluctuations in density. Over time, gravity amplified these fluctuations, pulling matter from underdense regions into overdense regions. The voids are the result of this process. They are regions that were slightly less dense in the early universe, and from which matter has been steadily draining for billions of years. The galaxies that might have formed in these regions never did, because the gas and dark matter that would have coalesced into galaxies was pulled away toward the surrounding filaments and clusters. This means the voids are not truly empty. They contain dark matter, though in very low concentrations. They contain gas, though it is extremely diffuse and difficult to detect. They may even contain a few small galaxies that formed before the matter drain became too severe. But in terms of visible structure, the galaxies and clusters that define the cosmic web, the voids are as close to empty as the universe gets. The matter is still there, in some abstract sense, but it has been redistributed so thoroughly that the voids have become vast regions of near-nothingness. The term void also allows astronomers to discuss these regions comparatively. Not all voids are the same. Some are small, perhaps 20 or 30 million light-years across. Others are enormous, stretching for hundreds of millions of light-years. Some voids are relatively isolated, surrounded by dense walls of galaxies. Others are interconnected, forming networks of emptiness that thread through the cosmic web. Some voids are nearly spherical, others are elongated or irregular. By naming these regions and cataloguing their properties, astronomers can begin to understand the processes that created them and the role they play in the larger structure of the universe. There is also a philosophical dimension to naming nothing. When we give something a name, we're asserting that it exists in a meaningful way. The voids exist. They are real features of the universe, as real as galaxies or stars. But they are defined entirely by absence. They are regions where we do not find what we expect to find. In a sense, naming the voids is an admission that absence itself can be a thing, that the lack of galaxies is as much a part of cosmic structure as the presence of galaxies. The universe is made not only of matter but of the spaces between matter, and those spaces are vast enough and structured enough to deserve names of their own. The invention of the term void also reflects a broader truth about scientific understanding. We cannot study what we cannot name. Language shapes thought, and by creating a term for these empty regions, astronomers gave themselves the conceptual tools to investigate them systematically. Before the voids had a name, they were just puzzling gaps in galaxy surveys. After they had a name, they became objects of study. Surveys were designed specifically to map voids. Simulations were run to understand how voids form and evolve. Theories were developed to explain their sizes, shapes, and distributions. The name gave the phenomenon reality in the scientific discourse, and yet the name also carries a certain irony. We call them voids, which suggests emptiness, but they are not truly empty. We define them by what they lack, but their importance comes from what they reveal about the universe's structure. The voids are the regions where gravity has evacuated matter most thoroughly, and by studying them, we learn how gravity shapes the cosmos at the larger scales. They are absences that teach us about presence, empty spaces that illuminate the processes that fill other spaces with galaxies and stars. The name void is accurate, but it is also incomplete. These regions are empty, yes, but they are also enormous, structured, and essential. They are the background against which the rest of the universe is written, the silence between the notes, the canvas beneath the paint. By naming nothing, astronomers acknowledge that the universe is not just made of things. It is also made of the relationships between things, the distances that separate them, the structures that organize them. The voids are part of that structure. They are the negative space that defines the positive space, the emptiness that gives meaning to the fullness. And in naming them, we admitted that emptiness, at cosmic scale, is something worth studying, worth understanding, worth giving a place in our maps of the universe. The realization that voids were not random gaps but organized structures came gradually, through the painstaking work of mapping galaxies in 3 dimensions. For most of the 20th century, astronomers catalogued galaxies by their positions on the sky, recording their angular coordinates and brightness but lacking precise information about their distances. This created a 2-dimensional picture of the universe, as if you were looking at a city from far above and seeing only the rooftops without knowing which buildings were close together and which were separated by miles of empty space. The breakthrough came with redshift surveys. By measuring how much the light from each galaxy had been stretched by the expansion of the universe, astronomers could determine how far away each galaxy was. This added the 3rd dimension to their maps. Galaxies that appeared close together on the sky might turn out to be separated by vast distances, while galaxies that appeared far apart might actually be neighbours in 3-dimensional space. As these surveys expanded through the 1970s and 1980s, covering more and more galaxies across larger and larger volumes of space, a pattern began to emerge. Galaxies were not scattered randomly, they formed structures. Long filaments of galaxies stretched across hundreds of millions of light years. Flat sheets of galaxies extended like walls through space. And surrounding these filaments and sheets were the voids, enormous regions where almost no galaxies could be found. The universe was not a uniform distribution with local clumps. It was a cosmic web, a network of matter surrounding emptiness. The first major wall discovered was the Coma Wall, also called the Great Wall, mapped in detail in the late 1980s. It is a sheet-like structure of galaxies stretching roughly 500 million light-years across, and 200 million light-years wide, but only about 15 million light-years thick. Imagine a wall so vast that light takes 500 million years to travel along its length, yet so thin relative to its other dimensions that it is almost like a sheet of paper at cosmic scale. This wall is not a solid object. It is a concentration of thousands of galaxies arranged in a flat distribution, like cities along a coastline, bordering an enormous void on one side. The discovery of the Great Wall was startling because it revealed structure at scales far larger than anyone had anticipated. Before this, the largest known structures were galaxy clusters and superclusters, which were already enormous, spanning tens of millions of light years. But the Great Wall was an order of magnitude larger. It suggested that the universe was organized into structures hundreds of millions of light years across, structures so large that they challenged the assumption that the universe should appear smooth and uniform at large scales. But more important than the wall itself was what the wall implied about the voids. The voids were not isolated bubbles of emptiness scattered randomly through space. They were bounded by walls and filaments. The galaxies concentrated along the surfaces of the voids, like soap bubbles clustering at the intersections of foam. The voids themselves were the interiors of these bubbles, vast volumes of space almost entirely devoid of galaxies. The walls were the boundaries, the interfaces between void and void, the thin regions where matter had been gravitationally compressed as it drained away from the empty regions. This pattern repeated everywhere astronomers looked. Every void was surrounded by overdense regions. Every filament bordered at least one void. The structure was not chaotic. It was organized, coherent, and remarkably uniform in character across the entire observable universe. The cosmic web was not a metaphor. It was an accurate description of how matter actually arranges itself at the larger scales. The walls form because of how gravity works over cosmic time. In the early universe, matter was distributed almost uniformly, but with tiny variations in density. Regions that were slightly denser than average began to attract matter from their surroundings. Regions that were slightly less dense began to lose matter to their neighbours. This process was not symmetrical. Matter did not just move toward dense regions in a simple radial pattern. It flowed along the paths of least resistance, pulled by the combined gravitational influence of all the surrounding matter. The result was that matter streamed along filaments toward the nodes where filaments intersected, and it drained out of the regions between filaments, creating the voids. As matter flowed out of what would become the voids, it did not spread evenly into the surrounding space. It concentrated along the surfaces, the boundaries of the voids, because this was where the gravitational pull from multiple directions balanced out. If you were a particle of gas in the early universe, and you were being pulled toward a dense filament on one side, and another dense filament on a different side, you would end up somewhere between them, on the wall that separated two voids. Over billions of years, this process created the sheet-like walls we observe today, thin concentrations of galaxies marking the boundaries between vast empty regions. The discovery of these walls also changed how astronomers thought about the voids themselves. Before the walls were understood, voids seemed like anomalies, strange regions where galaxies had failed to form for unclear reasons. But once the walls were mapped, it became clear that the voids were not failures of galaxy formation. They were the natural consequence of gravitational collapse on the larger scales. The walls and the voids are two sides of the same process. Matter concentrates in walls because it evacuates from voids. The voids grow empty because the walls grow dense. You cannot have one without the other. This also meant that the voids are not permanent features in the sense of being unchanging. They grow over time. As the universe expands and matter continues to flow along filaments toward clusters, the voids become larger and emptier. The walls become denser and more pronounced. The process that created the cosmic web is still ongoing, and it will continue for billions of years into the future. The voids we observe today are not finished structures. They are growing. The emptiness is deepening. Understanding the walls also revealed something about the geometry of cosmic structure. The voids are not perfect spheres. They are irregular, shaped by the distribution of matter around them and by the history of how they formed. Some voids are elongated, stretched along the direction of nearby filaments. Others are more spherical, bounded on all sides by relatively uniform walls. Still others are interconnected, with narrow channels linking one void to another, creating a network of emptiness threading through the cosmic web. The walls themselves are not uniform either. They vary in density and thickness. Some walls are rich in galaxies, containing dense clusters and bright concentrations of matter. Others are sparse, barely distinguishable from the voids they border. The densest regions of the walls are where filaments intersect, where matter has been funneled from multiple voids into a single location. These intersections often coincide with the richest galaxy clusters, the largest concentrations of matter in the universe. There is a certain beauty to this structure when you visualize it properly. The cosmic web resembles foam, with galaxies concentrated along the thin surfaces and emptiness filling the interiors. But it also resembles a neural network, with filaments connecting nodes and information flowing along the connections. The analogy is not perfect, but it captures something true about the organization. The universe is not random. It is structured, and that structure has a logic to it, a geometry determined by gravity and time. The wall discovery also forced astronomers to reconsider the concept of large-scale homogeneity. The cosmological principle states that the universe, when viewed at large enough scales, should appear uniform in all directions. No location should be special. No region should be fundamentally different from any other. But the walls and voids seem to violate this principle, at least at scales of hundreds of millions of light years. The universe did not look uniform at these scales. It looked highly structured. The resolution to this apparent contradiction is that the structure repeats. The cosmic web is not unique to our region of space. It exists everywhere. Every part of the observable universe shows the same pattern of filaments, walls, and voids. The structure is uniform in character, even though the specific arrangement of voids and walls varies from place to place. When you average over large enough volumes, encompassing many voids and many walls, the average density does become uniform. The cosmological principle holds, but only when you look at scales large enough to encompass multiple complete units of the web structure. This means the voids are not exceptional, they are typical. Most of the universe's volume is voids. The walls are the exception, thin surfaces enclosing vast volumes of emptiness. We happen to live in a galaxy that formed within one of these thin surfaces, on the edge of a void rather than within it. This location is not special. Most galaxies are in walls or filaments, simply because that is where galaxies form. But it does mean that our view of the universe is shaped by our location within the structure. We see the cosmic web from within one of its thin strands, looking outward at the surrounding voids and across to other strands beyond them. The discovery of the walls transformed the voids from curiosities into essential components of cosmic structure. The voids are not gaps in the universe. They are the primary feature, and the walls are the boundaries. The universe is mostly emptiness, organized into vast interconnected volumes, separated by thin surfaces where galaxies gather. Understanding this structure is essential to understanding the universe itself, because the structure determines how matter flows, how galaxies form, and how the cosmos will evolve over time. The walls define the voids, and the voids define the walls. Neither can be understood in isolation. If you fill a sink with water and add soap, then agitate the water to create bubbles, you will produce foam. The foam consists of air pockets surrounded by thin films of soapy water. The bubbles are not uniform in size. Some are large, some are small. They press against each other, deforming into polyhedral shapes rather than perfect spheres. The soap concentrates along the edges where bubbles meet, forming a network of thin films and narrow channels. Most of the volume is air. The soap and water occupy only the boundaries. This is the structure of the universe at the larger scales. The cosmic web is foam. The voids are the air pockets, vast volumes of nearly empty space. The filaments and walls are the soapy films, thin concentrations of galaxies surrounding the voids. And just as foam is mostly air with only a small fraction of its volume occupied by liquid, the universe is mostly voids with only a small fraction of its volume occupied by galaxies and clusters. The analogy is not perfect, but it captures the essential architecture more accurately than any other comparison. The foam structure was not predicted before it was observed. Early cosmological models assumed that matter would distribute itself more evenly, perhaps clustering into isolated groups and clusters, but without the large-scale organization we now know exists. The discovery that galaxies arrange themselves like foam was unexpected, and it required new theoretical frameworks to explain. The explanation lies in how gravity amplifies small initial fluctuations in density over billions of years, creating a pattern that naturally resembles foam, even though no surface tension or liquid is involved. In soap foam, bubbles form because surface tension minimizes the area of the liquid films. Air separates into distinct pockets, and the soap arranges itself along the surfaces to enclose these pockets in the most efficient way possible. In the cosmic web, a similar process occurs but driven by gravity rather than surface tension. Matter collapses along the paths of steepest gravitational gradient, which naturally creates filaments connecting dense nodes. The regions between filaments become voids, and the filaments themselves form the edges of polyhedral cells, just like the edges of bubbles in foam. The size of the bubbles in cosmic foam varies, but there is a characteristic scale. Typical voids are roughly 100 million light-years across. Some are smaller, perhaps 50 million light-years. Others are much larger, stretching 200 or 300 million light-years or more. But most fall within a relatively narrow range. Just as most bubbles in soap foam fall within a similar range of sizes, even though some are noticeably larger or smaller than average. This characteristic scale is determined by the initial conditions of the universe, the size of the density fluctuations imprinted during the first moments after the Big Bang, and by the amount of time that has passed since then. The bubbles are not isolated, they connect to each other. Where 3 bubbles meet, a filament forms. Where 4 or more bubbles meet, a dense node forms, often corresponding to a rich galaxy cluster or supercluster. The entire structure is interconnected, with no void completely surrounded by walls. There are always channels, narrow regions where one void connects to another, allowing the structure to extend across the entire observable universe without interruption. The cosmic web is a single continuous structure, not a collection of separate pieces. This interconnectedness has important implications for how the structure formed and how it continues to evolve. Matter does not just drain out of voids into the nearest wall. It flows along filaments toward the densest nodes, following the gravitational gradients created by the entire surrounding distribution of matter. A particle of gas in the early universe would have felt gravitational pulls from multiple directions simultaneously, and its trajectory would have been determined by the balance of all these forces. Over time, this led to the organized flow of matter along preferred paths, creating the filaments and evacuating the voids. The foam architecture also explains why voids are not perfectly spherical. If voids formed in isolation, each one growing independently, they would tend to be more round. But because voids grow in the presence of other voids, they press against each other and deform into irregular shapes. A void bounded by other voids on all sides will be roughly polyhedral, with flat walls where it meets its neighbours and elongated dimensions where it extends into less constrained regions. The shapes of voids are determined by their neighbours, just as the shapes of bubbles in foam are determined by the bubbles surrounding them. There is also a hierarchy to the foam structure. Large voids contain smaller substructure. Within a large void, you might find smaller voids, or filaments threading through the interior, or small groups of galaxies that formed before the void became too empty to support further galaxy formation. This nested structure is similar to how large bubbles in foam sometimes contain smaller bubbles within them, or how the films between bubbles can themselves develop substructure. The universe is not organized into a single level of foam. It is a fractal-like pattern, with structure at multiple scales, though the most prominent scale is the 100 million light-year voids. The comparison to foam also helps clarify what it means for the universe to be mostly empty. When you look at soap foam, you immediately recognize that most of what you're seeing is air. The soap is just the thin boundaries. Similarly, when you look at the cosmic web, most of what you're looking at is voids. The galaxies are just the thin boundaries. But because we live in one of those boundaries, and because our telescopes naturally focus on the bright objects, the galaxies and stars, rather than the dark voids, our perception is biased. We see the foam structure from the inside, from within one of the thin films, and so we tend to think of the galaxies as the primary feature and the voids as secondary. But in terms of volume, the voids are primary. They occupy most of the space. Quantifying this precisely is difficult because the boundaries between voids and filaments are not sharp. There is no clear line where a void ends and a filament begins. Galaxy density decreases gradually as you move from a filament into a void, not abruptly. But even with this ambiguity, estimates suggest that voids occupy somewhere between 60 and 80% of the universe's volume. The exact number depends on how you define the boundary of a void, but the conclusion is clear either way. Most of the universe is voids. The filaments, walls, and clusters occupy only a small fraction of the total volume, even though they contain most of the galaxies. This distribution has remained roughly constant over cosmic history, though the details have changed. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly. There were no voids yet and no filaments. The density fluctuations that would eventually grow into the cosmic web were present, but they were tiny, less than 1 part in 100,000. Over time, gravity amplified these fluctuations. Regions that were slightly denser attracted more matter. Regions that were slightly less dense lost matter. The contrast grew. By the time the universe was a few billion years old, the foam structure had begun to emerge, voids were starting to form, and filaments were starting to concentrate. By the time the universe reached its current age of nearly 14 billion years, the structure had matured into the foam we observe today. But the process is not finished. The voids are still growing. As the universe continues to expand, and as dark energy drives the acceleration of that expansion, the voids will become larger and emptier. The filaments will thin as matter continues to flow along them toward the densest clusters. The foam will become more pronounced, with sharper contrasts between the dense nodes and the empty voids. In the far future, billions of years from now, the universe will be even more dominated by voids than it is today. The foam architecture will remain, but it will be stretched and exaggerated by the relentless expansion of space. There is something unsettling about recognizing that the universe is structured like foam. Foam is ephemeral, it is fragile, it dissipates quickly, the bubbles pop, the structure collapses. But the cosmic foam is not fragile. It is held together by gravity, not surface tension, and it will persist for timescales far longer than human comprehension allows. The voids will not pop. The filaments will not collapse, at least not in the way soap films collapse. The structure is stable, or at least as stable as anything can be in an expanding universe. It will change over time, but it will not disappear. The foam architecture also suggests something about the fundamental nature of structure in the universe. Structure does not mean uniformity. It does not mean that matter fills space evenly. Structure means organization, pattern, predictability. The cosmic web is highly structured precisely because it is so non-uniform. The voids and filaments are not random. They follow rules. They form in predictable ways based on the initial conditions and the laws of gravity. The foam is the natural outcome of those laws acting over billions of years on a nearly uniform initial distribution. And finally, the foam architecture reminds us that the universe is not designed for our convenience or intuition. We live in a thin film of galaxies surrounding a void, looking out at other thin films surrounding other voids. The structure we see is the structure that gravity creates when given time and space to work. It is not a structure optimized for life, or for visibility, or for easy comprehension. It is simply the structure that exists. And understanding it requires accepting that most of the universe is not like the small region we inhabit. Most of the universe is empty, organized into vast interconnected voids, bounded by thin surfaces where galaxies cluster. We are in the minority, living in the exception, surrounded by a cosmos that is mostly absence. Light is the fastest thing in the universe. Nothing moves through space more quickly. No signal can propagate faster. No information can travel from one location to another in less time than it takes light to make the journey. This is a fundamental limit imposed by the structure of space-time itself, and yet, when light crosses a void, it takes so long that the delay becomes cosmologically significant. Consider a photon emitted from a galaxy on one side of a typical void, travelling toward a galaxy on the other side. The void is 100 million light-years across. The photon, travelling at 300,000 kilometers per second, will take 100 million years to complete the journey. This is not a human timescale. It is not even a geological timescale. It is a cosmological timescale comparable to the time it takes for significant evolutionary changes to occur in galaxies, for stars to be born and die, for entire stellar populations to age. During those 100 million years, the universe itself changes. Galaxies evolve, stars form from collapsing gas clouds, burn through their fuel, and explode as supernovae. New generations of stars form from the remnants, spiral galaxies slowly consume their gas reserves and fade. Elliptical galaxies age passively, their stellar populations growing redder as the hottest stars exhaust their fuel and die. Black holes at the centres of galaxies accrete matter and emit radiation. Mergers occur between galaxies in dense clusters. The cosmic background radiation cools as the universe expands. All of this happens while the photon crosses the void. This means that when we observe a galaxy on the far side of a void, we are not seeing it as it is now. We are seeing it as it was when the light left, 100 million years ago. The galaxy we observe is younger than the galaxy that exists in the present moment. It contains stars that have since died. It lacks stars that have since formed. Its structure may have changed due to interactions with neighbouring galaxies or due to its own internal evolution. The void acts as a barrier not just in space but in time, separating our observation from the current state of the object we are observing. For nearby objects, this light delay is negligible. The Moon is about 1¼ light seconds away, so we see it as it was slightly more than a second ago. The Sun is 8 light minutes away, so we see it as it was 8 minutes ago. Even the nearest star beyond the Sun, Proxima Centauri, is only 4 light-years away, so the delay is just 4 years. These delays are real, but they are short enough that they do not significantly affect our understanding of these objects. The Moon, the Sun, and even nearby stars do not change much in seconds, minutes, or years, but voids introduce delays measured in millions or hundreds of millions of years. At these timescales, the delays are not negligible. They are central to how we understand the objects we observe. When astronomers study galaxies across a void, they are studying those galaxies in the past. The farther across the void, the deeper into the past they look. A galaxy on the near side of a void appears more recent than a galaxy on the far side, even if both galaxies are intrinsically similar. The void creates a gradient in time, with objects at different distances appearing at different stages of their evolution. This effect becomes even more pronounced when we consider supervoids, which can be several 100 million light-years across. Light crossing a supervoid might travel for 300 million years or more. 300 million years ago on Earth, the first reptiles were beginning to evolve. The supercontinent Pangaea had not yet formed. The climate and geography of the planet were utterly different from what they are today. A photon that left a galaxy on the far side of a supervoid 300 million years ago is only arriving now, carrying information about a galaxy as it existed in an era unimaginably remote by human standards. The light delay also means that events occurring in galaxies across a void are invisible to each other for enormous spans of time. If a supernova explodes in a galaxy on one side of a void, the light from that explosion will not reach a galaxy on the other side for 100 million years. Any observers in that distant galaxy, if they existed and were looking in the right direction, would not see the supernova until 100 million years after it occurred. They would be observing an event that is ancient history by the time it becomes visible to them. This creates a form of causal isolation. Events on one side of a void cannot influence events on the other side in any immediate sense. Light carries information, and information carries influence, but the influence is delayed by the travel time. A galaxy in the centre of a void is isolated not just spatially, but causally. It cannot interact with distant galaxies on timescales shorter than the light crossing time of the void. For all practical purposes, it exists in its own bubble of causality, disconnected from the rest of the universe except through signals that take hundreds of millions of years to arrive. This isolation is not symmetrical across the universe. Galaxies in dense clusters separated by only a few million light-years can interact on much shorter timescales. Light crosses the distance between them in millions of years rather than hundreds of millions. They can influence each other's evolution through gravitational interactions, through the exchange of gas, through tidal forces that trigger star formation or strip away outer regions. They are part of an interactive system, evolving together in a coordinated way. But galaxies separated by voids do not have this luxury. They evolve in isolation, shaped only by their own internal processes and by the gradual expansion of space around them. The light delay also affects how we map the structure of the universe. When we create a map showing the positions of galaxies, we are not mapping the universe as it is now. We are mapping the universe as it was at various times in the past, depending on how far away each galaxy is. Nearby galaxies appear as they were recently. Distant galaxies appear as they were long ago. The map is not a snapshot of a single moment in time. It is a composite of many different moments, layered on top of each other, with the most distant objects representing the most ancient light. This creates a subtle distortion in our perception of structure. The voids we observe are not the voids as they exist now. They are the voids as they existed when the light we are currently receiving was emitted. If a void is 100 million light-years across, and we are observing galaxies on the far side of it. We are seeing those galaxies as they were 100 million years ago, when the universe was slightly younger and the void was slightly smaller. The void has expanded since then due to the expansion of the universe itself. The galaxies have moved farther apart. The structure we observe is already out of date by the time we observe it. For the largest voids, this delay becomes comparable to significant fractions of the universe's age. A supervoid several 100 million light-years across represents light that has been travelling for a substantial portion of cosmic history. The galaxies we see on the far side of such a void are being observed at a significantly earlier stage of their evolution than galaxies nearby. The void becomes a window into the past, a way of observing how galaxies looked and behaved at earlier cosmic epochs. There is no way to eliminate this delay. It is built into the structure of space-time. Light travels at a finite speed, and distances are so large that travel times become enormous. We can account for the delay. We can model how galaxies should have evolved during the time their light has been travelling toward us. We can estimate what they look like now, even though we cannot observe them as they are now. But we cannot observe them directly in the present. The present, for objects across a void, is fundamentally inaccessible. We are limited to seeing the past. This limitation applies not just to us, but to any observer anywhere in the universe. A hypothetical civilization in a galaxy on the far side of a void from us would face the same limitation. They would see our galaxy as it was 100 million years ago, not as it is now. They would observe our past just as we observe theirs. The void separates us in time as well as space, creating a barrier that no technology can overcome because it is not a technological limitation. It is a limitation imposed by the speed of light and the size of the voids themselves. The light delay also reveals something profound about the nature of observation in cosmology. In most sciences, you can study an object in its present state. You can measure its current properties, observe its current behaviour, and draw conclusions based on what it is doing right now. But in cosmology, you can never observe the present state of distant objects. You can only observe their past states. The farther away an object is, the deeper into its past you see. This is not a flaw in our instruments or our methods. It is the nature of observing a universe where light travels at a finite speed and distances are measured in hundreds of millions of light years. The voids, then, are not just spatial structures. They are temporal structures as well, barriers that separate different moments in cosmic history. Crossing a void with your eyes, observing galaxies on the far side is equivalent to looking backward in time. The void enforces a delay between event and observation, a gap that can span hundreds of millions of years. And this delay is permanent. It cannot be reduced or eliminated. It is written into the geometry of the universe itself. The voids are not static. They do not remain the same size over time. They grow. This growth is not because matter continues to drain out of them, though that process does continue at a slower rate as the universe ages. The primary reason voids grow is because space itself expands within them. The expansion of the universe, which affects all of space, has a particularly pronounced effect inside voids because there is so little matter present to resist it through gravitational attraction. To understand this, you must first understand what cosmic expansion means. The universe is not expanding into anything. Space itself is expanding. The distance between any 2 points that are not gravitationally bound to each other increases over time, not because the points are moving through space, but because the space between them is stretching. This stretching affects everything at large scales, but its effects are only noticeable over distances of millions or billions of light years, where the cumulative stretching becomes significant. In regions where matter is densely concentrated, such as galaxy clusters, or even individual galaxies, gravity counteracts the expansion. The matter is bound together by its mutual gravitational attraction, and this binding is strong enough to prevent the expansion from pulling the structure apart. Our galaxy is not expanding. The local group of galaxies is not expanding. Even large galaxy clusters remain gravitationally bound and do not expand with the universe. But the distances between clusters, and especially the distances across voids, are not gravitationally bound. There is not enough matter present to hold these regions together against the expansion. Inside a void, where galaxy density is less than 10% of the cosmic average, and sometimes less than 1%, the gravitational forces are extremely weak. There is dark matter present, but even dark matter is sparse in voids compared to filaments and clusters. The expansion of space proceeds almost unopposed. The void grows larger as space stretches, and because there is so little matter to pull back against the expansion, the growth is nearly unimpeded. This means that a void which is 100 million light-years across today was smaller in the past and will be larger in the future. Exact numbers depend on the expansion rate of the universe, which has varied over cosmic history, but the principle is clear. Voids have been growing for billions of years, and they will continue to grow for billions more. The foam structure of the universe is not a fixed architecture. It is a dynamic structure, slowly stretching and expanding as time passes. The rate of expansion inside voids is determined by the Hubble constant, which describes how fast the universe is expanding at the current epoch. The Hubble constant is usually expressed in terms of how much the distance between 2 points increases per unit distance. Currently, space expands such that objects separated by about 3 megaparsecs, roughly 10 million light-years, are receding from each other at about 70 kilometers per second due to expansion alone. This does not sound like much, but over large distances the effect accumulates. Across a void 100 million light-years in diameter, the expansion causes the far side to recede from the near side at roughly 700 kilometers per second. This is not because the galaxies on the far side are moving through space at that speed. It is because the space between them is expanding at that rate. If you could somehow stop time and measure the void, then restart time and measure it again a million years later, you would find that it had grown by about 700 light-years in radius in every direction. The expansion is slow by human standards, but relentless. Over billions of years, this expansion has a profound effect on the structure of voids. A void that began as a modest underdensity in the early universe, perhaps only 20 or 30 million light-years across, has expanded over billions of years into a structure 100 million light-years across or more. The expansion does not create the void formed because matter drained out of underdense regions. But the expansion amplifies the void, making it larger and emptier over time. The voids we observe today are much larger than they were when the universe was young, and they will be even larger in the future. The expansion also affects the few galaxies that do exist inside voids. These galaxies are moving away from each other, carried apart by the expansion of space. If two small galaxies are located on opposite sides of a void, separated by 100 million light-years, they are receding from each other at hundreds of kilometers per second. They are not moving through space toward each other or away from each other in the conventional sense. The space between them is simply growing, increasing their separation over time. In the far future, they will be even farther apart, and the likelihood that they will ever interact gravitationally becomes vanishingly small. This creates a kind of feedback effect. As voids expand, the already sparse matter within them becomes even more diffuse. The few galaxies present become more isolated. The gravitational forces that might have slowed the expansion become weaker. The void becomes emptier and larger in a self-reinforcing process. This process will continue indefinitely as long as the expansion of the universe continues, and current observations suggest that the expansion is not just continuing, but accelerating. The acceleration is driven by dark energy, a mysterious component of the universe that exerts a kind of negative pressure, pushing space to expand faster over time. Dark energy dominates the universe's energy budget at the current epoch, making up roughly 70% of the total energy density. Matter, both normal and dark, makes up the remaining 30%. Because dark energy is uniformly distributed throughout space and does not clump like matter does, its effects are felt equally everywhere, but they are most noticeable in regions where matter is sparse. Inside voids, where there is little matter to counteract dark energy's influence, the expansion accelerates more freely. This acceleration means that voids are not just growing, they're growing faster over time. A void that expanded at a certain rate a billion years ago is expanding faster now, and it will expand even faster in the future. The rate of growth is increasing. In the distant future, billions of years from now, the expansion will have accelerated to the point where voids will dominate an even larger fraction of the universe's volume than they do today. The filaments and clusters will remain gravitationally bound, but the distances between them will increase dramatically. The cosmic web will stretch, and the voids will grow until they dwarf even the largest structures we currently observe. The expansion effect also has implications for what we can observe. As voids grow and the universe expands, distant galaxies recede from us faster and faster. Eventually, galaxies that are currently visible will recede beyond the cosmic horizon, the distance beyond which light cannot reach us because space is expanding faster than light can travel through it. This horizon is not a physical boundary. It is simply the limit of what we can ever observe, and it is determined by the expansion rate and the age of the universe. As the expansion accelerates, more and more galaxies will cross this horizon and disappear from view. Galaxies inside voids are particularly vulnerable to this effect because they are already isolated, and because the expansion within voids is relatively unimpeded. A galaxy in the centre of a large void, already separated from its nearest neighbours by vast distances, will eventually lose the ability to see those neighbours as they recede beyond the horizon. In the far future, such a galaxy will exist in a universe that appears almost entirely empty. It will see only itself and perhaps a few other very nearby dwarf galaxies, if any exist. The rest of the universe will have receded beyond reach, carried away by the relentless expansion of space. This future is not immediate. It will take tens of billions of years for the expansion to have this effect on most galaxies, but it is inevitable if the current understanding of dark energy is correct. The voids will expand indefinitely. The distances will grow without bound. The universe will become lonelier and emptier as time goes on, with galaxies increasingly isolated from each other, surrounded by voids that are ever larger and ever more devoid of light and matter. The expansion effect also changes how we interpret observations of voids. When we measure the size of a void, we are measuring it as it was in the past, because the light we observe took time to travel from the galaxies on the void's boundaries. By the time that light reaches us, the void has already grown larger due to expansion. The void we observe is not the void as it currently exists. It is the void as it existed when the light was emitted, which might have been tens or hundreds of millions of years ago. The current void is larger, though we cannot observe it directly. This also means that voids at different distances appear at different stages of their expansion. Nearby voids appear more recent, having expanded less since the light we observe left them. Distant voids appear more ancient, representing an earlier stage of cosmic structure, when voids were smaller and the universe was younger. By comparing voids at different distances, astronomers can study how voids have grown over time, tracing the history of expansion and understanding how the cosmic web has evolved. The expansion inside voids is not uniform in all directions. The exact rate depends on the distribution of matter around the void and on the geometry of the void itself. An elongated void might expand faster along its long axis than along its short axis. A void surrounded by dense walls of galaxies might expand more slowly than a void in a less dense region. These variations are subtle, but they are real, and they reflect the complex interplay between gravity and expansion at cosmic scales. Ultimately, the expansion effect reveals that voids are not permanent structures in the sense of being unchanging. They are dynamic, evolving features of the universe, growing larger and emptier as time passes. The cosmic web we observe today is a snapshot of a process that has been ongoing for billions of years and will continue for billions more. The voids are expanding, the structure is stretching, and the universe is becoming more dominated by emptiness with every passing moment. There are voids, and then there are supervoids. The distinction is not arbitrary. It is based on size, but also on the effects these structures have on the universe around them. A supervoid is not just a large void. It is a void so enormous that it begins to influence the light passing through it in measurable ways, creating observable signatures that allow astronomers to study these structures even when they cannot see the individual galaxies within them. A typical void might be 100 million light-years across. A supervoid can be 2 or 3 times larger, or even more. The largest known supervoids stretch across distances of nearly 1 billion light-years. To cross such a structure at the speed of light would take nearly 1 billion years, a duration comparable to the time since the first complex multicellular life appeared on Earth. These are not merely large voids. They are among the largest coherent structures in the observable universe. The scale is difficult to grasp even when stated in numbers. 1 billion light-years is a distance so vast that it exceeds any human reference point. The entire Milky Way galaxy, containing hundreds of billions of stars, is only about 100,000 light-years across. A supervoid is 10,000 times larger than our galaxy. The local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, spans roughly 10 million light-years. A supervoid is 100 times larger than that. Even the largest galaxy clusters and superclusters, which are themselves among the most massive structures in the universe, fit comfortably inside a supervoid with room to spare. What makes supervoids particularly significant is not just their size, but what that size implies about the distribution of matter in the universe. A supervoid represents a region where the density of matter is dramatically lower than average across an enormous volume. This is not a localized absence. It is a systematic underdensity extending across distances that encompass what would otherwise be dozens or hundreds of smaller voids and filaments. The existence of such structures suggests that the universe's large-scale structure is organized at even larger scales than the typical cosmic web pattern of filaments and voids. Supervoids form through the same processes that create smaller voids, but they represent regions where the initial underdensity in the early universe was more pronounced or more extended. Gravity drained matter from these regions just as it did from smaller voids, but because the initial underdensity covered a larger volume, the resulting void grew to a much larger size. Over billions of years, these regions have become vast near vacuums, with galaxy densities that can drop to just a few % of the cosmic average or even lower. The emptiness of a supervoid is profound. If you were placed in the center of one, the nearest galaxy might be hundreds of millions of light-years away in any direction. The darkness would be absolute. No stars would be visible. No galaxies would appear even in the most powerful telescopes until you looked outward across distances that light takes hundreds of millions of years to cross. You would exist in a sphere of emptiness so large that it would contain, in principle, enough volume to hold thousands of galaxies if matter were distributed at average cosmic density, but which instead contains perhaps a few dozen scattered across an almost incomprehensible expanse. Supervoids affect the light that passes through them. This effect is subtle but measurable, and it provides one of the primary ways astronomers can detect and study these structures. When light from the cosmic microwave background, the faint radiation left over from the Big Bang, passes through a supervoid, it loses a small amount of energy. This happens because the void is expanding as the light crosses it. The photon enters the void at one epoch, when the void has a certain size, and exits at a later epoch, when the void has grown larger due to cosmic expansion. The gravitational field of the void, which is weaker than average because the void contains less matter, changes slightly during the photon's transit. This change causes the photon to lose energy, which manifests as a slight decrease in temperature in the observed microwave background. This effect is called the integrated Sachs-Wolfe effect, and it creates a cold spot in the cosmic microwave background corresponding to the location of the supervoid. The cold spot is not dramatic. The temperature decrease is only a few millionths of a degree, but it is detectable with sensitive instruments. By mapping these cold spots, astronomers can identify supervoids even when the individual galaxies within them are too faint or too sparse to map directly. The supervoid announces its presence through the shadow it casts in the microwave background. Not all cold spots in the microwave background correspond to supervoids. The background has natural fluctuations, and some cold regions are simply random variations in the primordial density of the early universe. But the largest and most prominent cold spots often do correspond to supervoids, and by comparing the temperature maps of the microwave background with galaxy surveys, astronomers can confirm which cold spots are caused by voids and which are primordial. One of the most studied supervoids is the Eridanus supervoid, associated with a particularly large cold spot in the cosmic microwave background. This supervoid is estimated to be several hundred million light-years across, though the exact size is difficult to determine because its boundaries are not sharp. The cold spot it creates is one of the most prominent features in the microwave background, and it has been the subject of extensive study and some controversy. Some researchers have suggested that the cold spot is too large to be explained by a supervoid alone, and that it might represent an even more unusual structure or perhaps a statistical fluke. But the majority view is that it is consistent with a large supervoid affecting the microwave background through the integrated Sachs-Wolfe effect. Another notable supervoid is the KBC void, named after the astronomers who discovered it. This structure is even larger. possibly approaching 2 billion light-years in diameter. If this estimate is correct, the KBC void is one of the largest structures ever identified, comparable in size to the largest galaxy filaments and superclusters. The existence of such a structure raises questions about how the universe can produce underdensities of this magnitude, and whether our current models of cosmic structure formation are complete. The KBC void is also significant because we may be located relatively close to it, possibly even within its outer regions. If this is true, it would have implications for how we observe the rest of the universe. Our measurements of cosmic expansion, for example, depend on observing distant galaxies and measuring how fast they are receding from us. But if we are inside or near a large underdense region, the local expansion rate might be slightly different from the average expansion rate of the universe as a whole. This could introduce systematic errors into our measurements and affect our understanding of fundamental cosmological parameters like the Hubble constant and the density of dark energy. The scale of supervoids also affects their evolution. Because they are so large, the light crossing time is enormous. A signal travelling from one side of a supervoid to the other takes hundreds of millions of years. This means that different parts of the supervoid cannot coordinate their evolution in any direct sense. The expansion in one region of the void cannot influence the expansion in another region faster than the speed of light allows. The supervoid is too large to evolve as a single coherent structure on short timescales. It evolves instead as a collection of loosely connected regions, each responding to its local environment and to the gradual expansion of space. Over billions of years, supervoids grow larger just as smaller voids do, but their growth is more gradual in relative terms because the expansion rate, while constant in terms of kilometers per second per megaparsec, produces a larger absolute increase in size for larger structures. A supervoid that is 500 million light-years across grows by about 3.5 million light-years in radius every billion years, assuming the current expansion rate. This is slow, but over the age of the universe it accumulates into substantial growth. A supervoid that might have been a few hundred million light-years across when the universe was half its current age has expanded to nearly 1 billion light-years across today. The existence of supervoids also challenges some of our assumptions about the uniformity of the universe. The cosmological principle states that the universe should appear roughly the same in all directions when averaged over sufficiently large scales. But supervoids are large enough that they represent significant departures from uniformity, even at scales of hundreds of millions of light-years. If you were located in the centre of a supervoid, your view of the universe would be dramatically different from someone located in a dense supercluster. You would see far fewer galaxies, and the nearest structures would be much farther away. The universe would appear emptier and quieter. This raises the question of what scale is large enough for the cosmological principle to hold. If voids and supervoids introduce variations in density at scales of hundreds of millions of light-years, then the universe is only truly uniform when averaged over scales larger than this, perhaps 1 billion light-years or more. At smaller scales, the universe is lumpy, dominated by the foam structure of filaments and voids. Only when you step back far enough, encompassing many voids and many filaments, does the average density become uniform. Supervoids are rare compared to typical voids, simply because they require more extreme initial conditions to form. But they are not unique. Several have been identified, and more are likely to be discovered as galaxy surveys expand and deepen. Each supervoid is slightly different in size, shape and density, but they all share the common feature of being enormous underdense regions that stand out against the cosmic web. They are the deepest valleys in the landscape of cosmic structure, the places where matter is most conspicuously absent. Understanding supervoids is essential to understanding the full range of structure in the universe. They represent the extreme end of the spectrum, the largest and emptiest regions that gravity and expansion can create. They test the limits of our models of structure formation and force us to confront the fact that the universe contains structures at scales we are only beginning to map and comprehend. The supervoids are not just large voids, they are windows into the universe's largest scale architecture, revealing how emptiness can organize itself into coherent structures spanning nearly 1 billion light-years. In 2004, astronomers analyzing data from the Wilkinson Microwave Anisotropy Probe noticed something unusual in the cosmic microwave background. The microwave background is the faint radiation left over from the Big Bang, a nearly uniform glow that fills the entire sky with a temperature of about 2.7 degrees above absolute zero. The temperature is not perfectly uniform. There are tiny fluctuations, variations of a few millionths of a degree, that represent the seeds of all cosmic structure. But in one particular region of the sky, in the direction of the constellation Eridanus, there was a cold spot significantly larger and colder than the typical fluctuations. The cold spot is not small. It spans roughly 5 degrees across the sky, which is about 10 times the angular diameter of the full moon. This angular size corresponds to a physical region hundreds of millions of light-years across in the direction we are looking. The temperature in this region is about 70 millionths of a degree colder than the surrounding microwave background. This might not sound significant, but in the context of the microwave background, where most fluctuations are only a few millionths of a degree, a deficit of 70 millionths of a degree is substantial. It is one of the largest anomalies in the entire microwave sky. When the cold spot was first detected, it generated considerable attention and speculation. Some researchers suggested it might be a statistical fluke, a random fluctuation that happened to be larger than expected, but which did not represent any underlying physical structure. The microwave background contains millions of points on the sky, and with enough points, occasional large deviations from the average are inevitable even in a perfectly random distribution. But as more data accumulated and the cold spot persisted in higher resolution maps, the fluke explanation became less convincing. The cold spot is real, and it requires an explanation. The most plausible explanation is that the cold spot is caused by a supervoid. When light from the cosmic microwave background passes through a large underdense region, it loses a small amount of energy due to the integrated Sachs-Wolf effect. This energy loss manifests as a decrease in the photon's frequency, which corresponds to a decrease in temperature. A sufficiently large supervoid, hundreds of millions of light-years across and containing far less matter than average, would create exactly the kind of cold spot observed in Eridanus. Galaxy surveys conducted in the direction of the cold spot have confirmed the presence of a large underdense region. The Eridanus supervoid, as it has come to be called, is a volume of space where galaxy density drops to about 20% of the cosmic average or less. The exact size and depth of the void are difficult to determine because its boundaries are not sharp, and because mapping galaxy density in 3 dimensions requires precise distance measurements for thousands of galaxies. But the evidence is consistent with a supervoid several hundred million light-years across, centered roughly between us and the microwave background in that direction. If this interpretation is correct, then the cold spot is a shadow. It is the imprint of a vast absence, a region where the lack of matter has left a detectable signature in the most ancient light we can observe. The photons we detect as the microwave background were emitted nearly 14 billion years ago, shortly after the Big Bang, and they have been travelling through space ever since. When these photons passed through the Eridanus supervoid, they encountered a region where space was expanding slightly faster than average because there was less matter to slow the expansion through gravitational attraction. This caused the photons to lose energy, and by the time they reached us, they were slightly cooler than photons that travelled through denser regions. The process is subtle and depends on the timing. The supervoid is expanding as the photons cross it. When the photons enter the void, they fall into a gravitational potential well that is shallower than average because the void contains less matter. As they climb out of this well on the other side, they should in principle regain the energy they lost on the way in. But because the void expands while the photons are crossing it, the potential well is shallower when the photons exit than when they entered. The net result is that the photons lose a small amount of energy, which we observe as a cold spot. Not everyone agrees that the Eridanus supervoid fully explains the cold spot. Some analyses suggest that even a very large supervoid cannot account for the entire temperature deficit, and that the cold spot is colder than expected based on the observed galaxy density in that region. This discrepancy has led to alternative explanations, including the possibility that the cold spot represents a combination of a supervoid and a primordial fluctuation, or that it is influenced by some other unknown effect. A few researchers have even proposed more exotic explanations, such as a collision between our universe and another universe in a multiverse scenario, though these ideas are highly speculative and not widely accepted. The cold spot remains one of the most intriguing features in the cosmic microwave background. It is a visible manifestation of a supervoid, a direct way of observing the influence of vast empty regions on the light that passes through them. Most voids are invisible in the microwave background because they are either too small or not underdense enough to create a detectable temperature deficit, but the larger supervoids, like the one in Eridanus, are extreme enough that they leave a mark. There is something unsettling about the cold spot when you consider what it represents. It is not just a region of the sky that happens to be colder. It is a window through which we are looking at one of the emptiest regions in the observable universe. The light we see came from the early universe, passed through this enormous void, and arrived at our detectors carrying the signature of that passage. The cold spot is evidence of absence on a scale that challenges our intuition. It is a visible reminder that most of the universe is empty, and that this emptiness is structured and measurable. The cold spot also reveals the limitations of what we can observe directly. We cannot see the supervoid itself in visible light, because there are so few galaxies within it. We can only infer its existence from the galaxies on its boundaries, and from the effect it has on the microwave background. The void is invisible, but its influence is not. It casts a shadow in the most ancient light, a cold region in a nearly uniform glow, and through that shadow we can study a structure that is otherwise almost entirely dark. Other cold spots exist in the microwave background, and some of them may also be caused by supervoids. Astronomers have searched for correlations between cold regions in the microwave background and underdense regions in galaxy surveys, and they have found evidence for several such associations. Not every cold spot corresponds to a supervoid, and not every supervoid creates a detectable cold spot, but the relationship is real. Supervoids, by virtue of their size and emptiness, affect the light passing through them in measurable ways. The cold spot in Eridanus is the most prominent example, but it is not necessarily the largest supervoid. The KBC void, if it exists as described, may be even larger, but it does not produce as strong a signature in the microwave background because of its geometry and position relative to us. The cold spot effect depends not just on the size of the void, but on how the void is oriented along our line of sight, and on how underdense it is. A smaller but more extremely underdense void might produce a stronger cold spot than a larger but less underdense one. The existence of the cold spot also has implications for cosmology more broadly. It suggests that the universe contains structures at scales large enough to produce observable effects in the cosmic microwave background, which is one of the most uniform and well-studied datasets in astronomy. If supervoids can affect the microwave background, then they are part of the large-scale structure that must be accounted for in cosmological models. They are not mere curiosities. They are features of the universe that influence our observations and that must be understood if we are to have a complete picture of cosmic structure. The cold spot is also a reminder that the universe is not as uniform as it might appear at first glance. Yes, the microwave background is remarkably smooth, with temperature variations of only a few parts in 100,000. But embedded within that smoothness are larger-scale features, cold spots and hot spots created by the voids and overdensities that light encounters on its journey across the universe. The uniformity is real, but it is a statistical uniformity, an average over enormous scales. At any given location, the universe can deviate significantly from that average. In the end, the cold spot is both an observation and a mystery. It is clearly real, detected by multiple instruments and confirmed in multiple datasets. It almost certainly involves a supervoid, a vast underdense region hundreds of millions of light years across. But the exact details, the precise size of the void, its depth, its shape, and whether it alone explains the entire cold spot remain uncertain. The cold spot is a signature of one of the largest known absences in the universe, a shadow cast by emptiness across the most ancient light we can observe. It is evidence that the voids are not just large, they are large enough to leave marks on the cosmos itself. The largest structures in the universe bound by gravity are superclusters. These are vast collections of galaxy clusters, groups and filaments spanning hundreds of millions of light years. The Laniakea supercluster, of which our local group is a part, stretches roughly 500 million light years across and contains the mass of 100,000 trillion suns distributed among roughly 100,000 galaxies. It is an almost incomprehensibly large structure, a concentration of matter that dominates an enormous volume of space. But superclusters do not fill the universe. They are separated from each other by voids. Between one supercluster and the next lies a region where galaxies are scarce, where density drops dramatically, where the cosmic web thins into near-nothingness. These regions between superclusters are among the emptiest in the observable universe. They represent the largest gaps in the matter distribution, the places where the foam structure of the cosmos is most evident. To travel from one supercluster to another, you would have to cross these voids. There is no other path. The superclusters are not connected by dense bridges of galaxies. They are islands in an ocean of emptiness, separated by distances that light takes hundreds of millions of years to cross. The voids between superclusters are not fundamentally different from other large voids, but they are positioned at the largest scales of structure, marking the boundaries between the most massive gravitationally bound systems in the universe. Consider the distance between Laniakea and the nearest neighbouring supercluster of comparable size. This distance is several hundred million light-years. In between lies a void or a series of interconnected voids where galaxy density is a small fraction of the cosmic average. If you were travelling at the speed of light from the edge of Laniakea toward the next supercluster, you would spend the majority of your journey crossing these voids. For hundreds of millions of years, you would see almost nothing. The galaxies of Laniakea would recede behind you, and eventually become too faint to detect. The galaxies of the next supercluster would still be too far ahead to see. You would exist in darkness, surrounded by emptiness, with no reference points and no indication that you were moving at all. This isolation between superclusters is not temporary. It is permanent and growing. The universe is expanding, and as it expands, the distances between superclusters increase. The voids grow larger, the separation deepens. In the far future, billions of years from now, the superclusters will be even more isolated from each other than they are today. The voids between them will have expanded to such an extent that light from one supercluster will no longer be able to reach another because the expansion of space will carry them away from each other faster than light can travel between them. This future isolation is not speculation. It is a consequence of dark energy and the acceleration of cosmic expansion. Dark energy drives space to expand at an accelerating rate, and this acceleration means that distant structures are receding from us faster and faster over time. Eventually, structures that are currently visible will cross the cosmic horizon, the boundary beyond which their light can no longer reach us. Superclusters that are separated by the largest voids will be the first to lose contact with each other. The voids between them will expand until they become uncrossable, even by light. The voids between superclusters are also significant because they represent the largest coherent regions of underdensity in the universe. Within a supercluster, you can find smaller voids, regions where galaxies are less dense than average. But these voids are embedded within the larger structure of the supercluster. The voids between superclusters, by contrast, are not embedded within anything. They are the spaces that define where one large-scale structure ends and another begins. They are the true boundaries of the cosmic web at its largest scale. These voids contain almost nothing. A few scattered galaxies might be present, isolated systems that formed in the underdense regions and remained there as the voids expanded. But these galaxies are extremely rare. Most of the volume between superclusters is genuinely empty of visible matter, containing only diffuse gas and dark matter at densities far below the cosmic average. If you could somehow measure the total mass within a void between superclusters, you would find that it contains perhaps 1% or less of the mass you would expect if matter were distributed uniformly. The gas that does exist in these voids is extraordinarily diffuse. It is hydrogen and helium mostly, left over from the Big Bang and never incorporated into galaxies or stars. This gas is so sparse that it is nearly impossible to detect directly. It does not emit light because it is too cold and too diffuse to produce detectable radiation. It does not absorb light significantly because there is so little of it along any given line of sight. The only way to study this gas is through its subtle effects on light passing through it, such as absorption lines in the spectra of distant quasars or slight distortions in the cosmic microwave background. The dark matter in these voids is similarly sparse. Dark matter does not emit or absorb light, so it cannot be observed directly. It can only be inferred through its gravitational effects. In dense regions, dark matter's gravity is strong enough to bend light, creating gravitational lensing effects that can be measured. But in voids, dark matter is so sparse that its gravitational influence is negligible. The voids between superclusters are regions where even dark matter, which outweighs normal matter by a factor of 5 to 1 in the universe as a whole, is nearly absent. This absence of both normal and dark matter means that the voids between superclusters are as close to truly empty space as the universe gets. They are regions where the density approaches zero, where gravity is almost non-existent, where nothing happens for billions of years at a time. A particle of gas in such a void might drift for the entire age of the universe without encountering another particle. A photon crossing such a void might travel for hundreds of millions of years without interacting with anything at all. The voids between superclusters also highlight the hierarchical nature of cosmic structure. At the smaller scales, matter clumps into stars and planets. At slightly larger scales, stars clump into galaxies. Galaxies clump into groups and clusters. Clusters clump into superclusters. And superclusters are separated by voids. Each level of this hierarchy represents a different balance between gravity and expansion, between the tendency of matter to pull together and the tendency of space to stretch apart. At the scale of superclusters, this balance tips decisively toward expansion. Superclusters themselves are not gravitationally bound as single units. They are collections of smaller bound structures, galaxy clusters and groups, that happen to be relatively close together in space. But the superclusters as a whole are being pulled apart by the expansion of the universe. Over time, the galaxies within a supercluster will remain gravitationally bound to their local groups and clusters, but the clusters themselves will drift apart, carried by the expansion of space. The supercluster will dissolve, leaving behind isolated clusters separated by ever-growing voids. This dissolution is already beginning. The voids between superclusters are expanding, and the superclusters are stretching. The cosmic web is not a permanent structure. It is a transient pattern, visible only during a specific epoch of cosmic history, when the universe is old enough for structure to have formed but young enough that expansion has not yet pulled everything too far apart. In the far future, the web will have dissolved, the voids will dominate, and the universe will consist of isolated clusters and groups, each surrounded by an ocean of emptiness that is growing deeper with every passing billion years. The space between superclusters is also where the expansion of the universe is most directly observable. In dense regions where galaxies are gravitationally bound, the expansion is masked by local motions. Galaxies orbit each other, fall toward clusters, move along filaments. These motions can be larger than the expansion-driven recession, making it difficult to measure the expansion directly. But in voids, especially the voids between superclusters, there are no local motions to complicate the picture. The few galaxies present are simply receding from each other due to expansion, with no significant gravitational interactions to disturb the pattern. By studying these galaxies, astronomers can measure the expansion rate with fewer confounding factors. The voids between superclusters are also the quietest regions in the universe. In dense clusters, galaxies collide and merge, stars form and explode, black holes accrete matter and emit jets of radiation. There is constant activity, constant change, but in the voids, nothing happens. The few galaxies present evolve slowly and in isolation. There are no collisions, no mergers, no triggered bursts of star formation. The evolution is passive, driven only by the gradual consumption of gas and the aging of existing stars. The voids are regions of profound stillness, where cosmic time passes but little changes. This stillness is not emptiness in the colloquial sense. It is emptiness in the precise sense. It is the absence of matter and energy to such a degree that the region becomes almost indistinguishable from the vacuum of space itself. The voids between superclusters are the closest the universe comes to being truly void, to being the empty stage on which matter and energy perform, rather than the performance itself. And yet even this emptiness is not absolute. Space itself exists. It expands. It has properties such as its geometry and its energy density. The voids are not nothing. They are space, stretched to its thinnest, quietest, most vacant state. Between the superclusters lies the true scale of cosmic absence. These are not the small gaps between galaxies or the modest voids within clusters. These are the great emptinesses, the regions that define the limits of structure, the spaces that will grow until they encompass almost everything. The voids between superclusters are the future of the universe, expanding now, but destined to dominate completely when the last connections between distant structures finally break and the cosmos becomes a collection of isolated islands surrounded by infinite uncrossable darkness. When we talk about the universe, we instinctively think of galaxies, stars, planets, and the vast structures we can see or infer from observations. We think of matter. But the universe is not mostly matter. It is mostly space, and most of that space is voids. To understand how much of the universe is actually void, we need to calculate what fraction of the total volume contains galaxies at densities close to the cosmic average, and what fraction is underdense to the point of being essentially empty. The calculations are not straightforward because the boundaries of voids are not sharp. There is no clear line where a void ends and a filament begins. Galaxy density decreases gradually as you move from a dense region into a void, not abruptly. This makes it difficult to define precisely where a void starts and where it stops. Different researchers use different definitions, which leads to different estimates of how much of the universe's volume is occupied by voids. But despite these differences in methodology, the conclusion is always the same. Voids dominate the universe's volume. Conservative estimates suggest that voids occupy at least 60% of the universe's total volume. More aggressive estimates, using broader definitions of what constitutes a void, place the figure closer to 80% or even higher. The exact number depends on the threshold you choose for defining a void, whether you count only regions where galaxy density is less than 10% of average, or whether you include regions where density is up to 20 or 30% of average. But regardless of where you draw the line, the voids clearly occupy more than half of all space. This means that if you could select a random location in the universe with equal probability for all points in space, you would most likely find yourself inside a void. You would not be near a galaxy, you would not be in a filament or a cluster. You would be in a region where galaxies are rare or absent, where the nearest visible structure might be tens or hundreds of millions of light years away. The typical location in the universe is not like our location. The typical location is empty. Our galaxy, the Milky Way, resides in a filament on the outskirts of the Laniakea supercluster. We are not in the densest part of the cosmic web, we are not in a rich galaxy cluster, but we are also not in a void. We are in a moderately dense region, close enough to other galaxies that we can see them, close enough that gravitational interactions have shaped our galaxy's history. This location is statistically unusual. Most of the universe's volume does not look like this. Most of the universe is emptier. The matter percentage is even more striking when you consider not just volume, but the distribution of galaxies themselves. While voids occupy most of the volume, they contain very few galaxies. A void might occupy 10% of the volume of a large survey region, but contain less than 1% of the galaxies. The galaxies are concentrated in filaments and clusters, occupying a small fraction of the total volume, but containing the vast majority of the visible matter. The cosmic web is not evenly distributed. It is extremely concentrated along thin structures, leaving the bulk of space empty. If you were to calculate the average density of the universe by dividing the total amount of matter by the total volume, you would get a number that's very small. The universe contains, on average, roughly 1 hydrogen atom per cubic meter of space. This is an extraordinarily low density, far lower than the best vacuum we can create in laboratories on Earth. But even this average is misleading because it conceals the true distribution. In dense regions like galaxy clusters, the density might be 100 or 1,000 times higher than average. In voids, the density might be 10 or 100 times lower than average. The average density exists almost nowhere in reality. It is a statistical construct that smooths over the highly structured, highly non-uniform distribution of matter. The low matter percentage in voids also has implications for what can happen in these regions. Galaxies form when gas collapses under its own gravity, cooling and fragmenting into stars. But this process requires a minimum gas density to work efficiently. In voids, the gas density is so low that galaxy formation is suppressed. The few galaxies that do exist in voids formed early, before the voids became too empty, or they formed from gas that was slightly denser than the surrounding void, but still far less dense than the gas in filaments and clusters. These void galaxies are typically small, dim, and isolated. They are not the massive spiral or elliptical galaxies we see in denser regions. They are dwarfs, barely visible even in deep surveys. The matter percentage also reveals something about the efficiency of structure formation. The universe started with an almost uniform distribution of matter. Tiny fluctuations, less than 1 part in 100,000, were present in the early universe. Over billions of years, gravity amplified these fluctuations, pulling matter from underdense regions into overdense regions. The result is a universe where matter has concentrated dramatically in some locations and has almost completely evacuated others. This process was extraordinarily efficient. It took a nearly smooth initial distribution and turned it into a highly structured web in which most of the volume is empty, and most of the matter is concentrated in filaments and clusters. The voids represent the regions that lost in this process. They started out slightly less dense than average, and gravity systematically drained them of matter. The gas and dark matter that might have formed galaxies in these regions was pulled away toward denser surroundings. What remains is a relic of the initial underdensity, amplified and expanded over cosmic time into a vast region where almost nothing exists. The voids are the price the universe pays for having structure. You cannot concentrate matter in some regions without depleting it in others. The filaments and clusters exist because the voids exist. The structure is a zero-sum redistribution of matter from underdense regions to overdense regions. This redistribution is not complete. There is still matter in the voids, just very little of it. Dark matter is present, though in concentrations far below the cosmic average. Gas is present, though so diffuse that it is almost undetectable. A few galaxies are present, scattered sparsely across enormous distances, but the total amount of matter in voids is negligible compared to the total amount in filaments and clusters. If you summed up all the matter in all the voids in the observable universe, it would be a small fraction of the total matter. The voids occupy most of the volume but contain very little of the mass. There is also the question of dark energy, which is distributed uniformly throughout space rather than clumping like matter. Dark energy makes up roughly 70% of the total energy density of the universe. Matter, both normal and dark, makes up the remaining 30%, but dark energy is the same everywhere. It does not concentrate in filaments or deplete in voids. This means that in terms of total energy density, voids are not as empty as they might seem. They contain dark energy, which exerts a kind of negative pressure that drives the expansion of space. In fact, because voids contain so little matter, they are regions where dark energy's influence is felt most strongly. The expansion proceeds almost unopposed, unchecked by the gravitational pull of matter. In the far future, as the universe continues to expand and dark energy continues to drive that expansion, the matter percentage in voids will decrease even further. The few galaxies that currently exist in voids will become even more isolated as the distances between them increase. The gas that remains will be stretched even thinner. The voids will grow larger and emptier, and the fraction of the universe's volume that they occupy will increase. Eventually, almost the entire universe will be voids. The filaments and clusters will remain gravitationally bound, but they will be tiny islands in an ocean of emptiness that grows without limit. This future is billions of years away, but it is inevitable if our current understanding of dark energy is correct. The matter percentage in voids is already low, and it will only decrease. The universe is becoming emptier, not fuller, as time passes. The voids are winning. They are expanding, consuming more and more of the total volume, while the structures we think of as the universe, the galaxies, the stars, the clusters, become increasingly rare and isolated exceptions in a cosmos dominated by absence. The matter percentage is a measure of how thoroughly gravity has reorganized the universe. It started almost uniform with matter distributed nearly evenly. Now, it is highly non-uniform with matter concentrated in a small fraction of the volume and voids occupying the rest. This transformation is one of the most important processes in cosmic history, and it is still ongoing. The voids are still growing. The matter is still concentrating. The percentage of the universe that is genuinely empty is still increasing. And in the end, when the expansion has stretched space to its limit, and the last connections between distant structures have broken, the matter percentage in voids will approach zero, and the universe will be almost entirely void, with only the faintest remnants of structure clinging to gravity's weakening hold. The voids are not empty in the sense of containing nothing, but they are empty in the sense of containing almost nothing, and that almost is shrinking. The matter percentage in voids is already negligible. In the future, it will be even smaller. The universe is mostly voids now, and it will be even more so later. This is not a flaw or an accident. It is the natural outcome of how structure forms in an expanding universe. The voids are the majority, the matter is the minority, and we, living in a galaxy surrounded by other galaxies, are living in a rare and temporary exception to the universe's true character. For most of the universe's history, the majority of galaxies could not see each other. This is not a statement about technology or the sensitivity of instruments. It is a statement about distance, light travel time, and the structure of the cosmic web. Even if a galaxy had evolved intelligent life with perfect telescopes capable of detecting the faintest possible light, most other galaxies would have been invisible to them for billions of years, simply because the light had not yet had time to arrive. When the universe was young, shortly after the first galaxies formed roughly 13 billion years ago, the distances between structures were already substantial. The cosmic web was beginning to take shape. Matter was concentrating into filaments and clusters, and voids were starting to form as gas and dark matter drained from underdense regions. But the universe was smaller then. The voids were smaller. The distances between galaxy clusters were smaller, and yet even in this younger, more compact universe, galaxies in different parts of the cosmic web were separated by distances so great that their light had not yet reached each other. Consider a galaxy that formed 12 billion years ago in what would eventually become a large void. At the time of its formation, the void was not yet fully developed. There were other galaxies nearby, though nearby meant tens or hundreds of millions of light years away. The light from those neighbouring galaxies began travelling toward this galaxy, but it travelled at a finite speed. While the light was in transit, the universe continued to expand. The distances grew larger. The void deepened. By the time the light from neighbouring galaxies finally arrived, those galaxies had receded even farther away, and the void between them had grown larger and emptier. For the first few billion years of this galaxy's existence, it would have been almost completely alone in its observable universe. The light from the nearest galaxies would not have arrived yet. The galaxy would have seen only itself, possibly a few very nearby dwarf companions, and the faint glow of the cosmic microwave background. No other major structures would have been visible. No distant galaxy clusters. No bright quasars. Just darkness in every direction beyond the immediate vicinity. This isolation was not unique to void galaxies. Even galaxies in denser regions experienced it. A galaxy forming in what would become a rich cluster might have had more neighbours within a relatively small volume, but galaxies in distant clusters separated by hundreds of millions of light years would still have been invisible to each other for billions of years. The light simply had not had time to cross the distances involved. The universe was full of galaxies, but each galaxy's observable universe was small, limited to a sphere whose radius was determined by the age of the universe and the speed of light. As the universe aged, this isolation gradually diminished. Light from more and more distant galaxies arrived. The observable universe for each galaxy expanded. Structures that had been invisible became visible. Galaxies that had been evolving in isolation began to see their neighbours, but this process was slow. For a galaxy 12 billion years old, it might have taken 3 or 4 billion years before the light from galaxies in neighbouring clusters arrived. For a galaxy in a void, it might have taken even longer. This historical isolation has profound implications for how we understand the universe. When we observe distant galaxies, we're seeing them as they were billions of years ago. But those galaxies, at the time we are observing them, could not see us. The light from our galaxy had not yet reached them. We were invisible to them, just as they were invisible to us, until their light finally arrived. The universe is full of these one-way observations, where one galaxy can see another but not vice versa, simply because the light has only travelled in one direction so far. The isolation also means that for much of cosmic history, most galaxies evolved without any knowledge of the larger structure they were embedded in. A galaxy in a filament could see nearby galaxies in the same filament, but it could not see the voids on either side or the filaments beyond those voids. Its view of the universe was limited to its immediate surroundings. It had no way of knowing that it was part of a cosmic web, no way of knowing that the web had a particular structure and geometry. The knowledge of large-scale structure came only later, as light from more distant regions finally arrived and revealed the broader pattern. This isolation was even more extreme for galaxies inside voids. These galaxies formed in regions that were already underdense and becoming more so over time. The nearest neighbouring galaxies were hundreds of millions of light years away, and the light from those neighbours took hundreds of millions of years to arrive. For most of the history of a void galaxy, it would have appeared to be alone in the universe. It would have had no evidence that other galaxies existed at all, except perhaps the cosmic microwave background, which would have told it that the universe had a history and was not always empty. But the microwave background does not show galaxies. It shows only the smooth glow of the early universe. A void galaxy would have had to wait billions of years, perhaps longer, before the first light from a distant galaxy arrived and revealed that it was not truly alone. We can estimate how long this isolation lasted by calculating light travel times across typical void distances. A void galaxy separated from the nearest filament by 100 million light-years would have remained isolated from that filament for at least 100 million years, and likely longer due to the expansion of space during that time. A galaxy in the centre of a supervoid, separated from the nearest dense structures by several hundred million light-years, might have remained isolated for half a billion years or more. During all that time, it would have evolved in silence, with no light from the outside universe to tell it that anything existed beyond its own small corner of space. The isolation also affected how galaxies evolved. Galaxies in dense clusters interact with each other frequently. They collide and merge, they exchange gas, they trigger bursts of star formation through tidal forces. These interactions shape their evolution and determine their final structure. But isolated galaxies, especially those in voids, experience none of this. They evolved passively, consuming their gas at their own pace, forming stars slowly and steadily without the dramatic events that characterize galaxies in denser environments. The isolation shaped their character. They are smaller, dimmer, and less active than galaxies in clusters, not because they are fundamentally different, but because they never had the interactions that drive galaxy evolution in denser regions. There is also a temporal asymmetry to consider. The isolation was most severe in the early universe, when distances were growing rapidly and light had not yet had time to cross even moderate voids. As the universe aged, more and more galaxies became visible to each other. The isolation lessened, but it never disappeared entirely. Even today, there are galaxies so far apart that they cannot see each other. Their light has not yet had time to cross the distance between them, and depending on the expansion rate and the acceleration driven by dark energy, it may never have that time. Some galaxies will remain forever invisible to each other, separated by distances that light cannot cross before the expansion of space carries them beyond each other's cosmic horizons. This creates a kind of historical fragmentation of the universe. Different regions had different observable universes at different times. A galaxy in one part of the cosmic web saw a different sky than a galaxy in another part, even if they existed at the same cosmic time, simply because the light reaching them came from different sources at different distances. The universe was not a single coherent entity that all galaxies experienced simultaneously. It was a patchwork of overlapping observable regions, each galaxy at the centre of its own sphere of visibility, with those spheres gradually expanding and overlapping as light travelled and the universe aged. The historical isolation also means that our current view of the universe is not complete, and it never will be. We see galaxies as they were in the past, at various distances and various times. The most distant galaxies we observe existed when the universe was only a few 100 million years old. We are seeing them in their infancy, shortly after they formed. But those galaxies, if they still exist, are now billions of years older and have evolved far beyond the state we observe. We cannot see them as they are now. The light from their current state has not yet reached us, and depending on the expansion rate, it may never reach us. This incompleteness is not a failure of observation. It is a fundamental feature of a universe with a finite age and a finite speed of light. The observable universe is limited. Beyond a certain distance, we cannot see anything because the light has not yet had time to arrive. And because the universe is expanding, the boundary of the observable universe is constantly moving outward, but it is also receding in another sense. Galaxies that are currently visible are moving away from us due to expansion, and some of them will eventually recede beyond the cosmic horizon and disappear from view. The historical isolation of the past is becoming the future isolation as well. For most of cosmic history, galaxies could not see most other galaxies. They evolved in partial ignorance, aware only of their immediate surroundings and blind to the larger structures beyond. This isolation shaped their evolution and limited their interactions. And even now, billions of years later, the isolation persists in a different form. We can see more than any galaxy in the early universe could see, but we still cannot see everything. We still cannot see the current state of distant galaxies. We are still limited by light travel time and the expansion of space. The historical isolation has lessened, but it has not ended, and in the far future, it will return stronger than ever as the expansion of space carries distant structures beyond the reach of light, and the universe fragments into isolated regions that can never communicate or observe each other again. The voids are growing, and they will continue to grow. This is not speculation. It is a consequence of the expansion of the universe and the nature of dark energy. The distances between galaxy clusters are increasing. The voids between them are becoming larger and emptier, and as time passes, this process will accelerate, driven by dark energy's relentless push against gravity's weakening pull. Dark energy is the dominant component of the universe's total energy density. It makes up roughly 70% of everything, and unlike matter, which clumps and clusters, dark energy is distributed uniformly throughout space. It exerts a kind of negative pressure, an outward push that drives the expansion of space to accelerate rather than slow down. This acceleration was discovered in the late 1990s through observations of distant supernovae, and it has been confirmed by multiple independent measurements since then. The expansion of the universe is not coasting, it is speeding up. The acceleration means that the voids will expand faster and faster over time. A void that is currently 100 million light-years across will be larger in 1 billion years, and larger still in 10 billion years. The expansion is gradual in the short term, but over billions of years it accumulates into dramatic changes. The cosmic web, which is currently visible and mappable across billions of light-years, will stretch and thin until it becomes unrecognizable. The filaments will pull apart, the clusters will become isolated, and the voids will dominate an ever larger fraction of the universe's volume. This future separation is already beginning. Galaxy clusters that are currently bound together by gravity will remain bound, but the distances between clusters will increase. Clusters that are currently separated by several 100 million light-years will eventually be separated by billions of light-years, then tens of billions, then more. The voids between them will grow until they become uncrossable, even by light. This is not because anything is preventing light from travelling through the voids. It is because the expansion of space within the voids will be so rapid that light emitted from one cluster toward another will never catch up. The space between the light and its destination will expand faster than the light can cross it. This creates a cosmic horizon, a boundary beyond which nothing can be observed, because the light from those regions can never reach us. The horizon is not a physical barrier. It is a limitation imposed by the expansion rate. Objects beyond the horizon are receding from us faster than the speed of light, not because they are moving through space that fast, but because the space between us and them is expanding that fast. And as dark energy continues to drive the acceleration, the horizon will move inward. Galaxies that are currently visible will eventually cross the horizon and disappear from view. The observable universe will shrink, even as the universe itself continues to expand. For galaxies in voids, this future is even more immediate. Void galaxies are already isolated, separated from their nearest neighbours by enormous distances. As the voids expand, these distances will increase. The few neighbouring galaxies that a void galaxy can currently see will recede farther and farther away, becoming dimmer and dimmer as the light redshifts and the expansion carries them toward the horizon. Eventually, those neighbours will cross the horizon and disappear. The void galaxy will be left alone, surrounded by darkness in every direction, with no other galaxies visible anywhere in its sky. This isolation is not temporary, it is permanent. Once a galaxy crosses the cosmic horizon, it is gone forever. No signal from it can ever reach the isolated galaxy again. No light, no gravitational wave, no information of any kind can traverse the expanding space between them. The isolation is absolute and irreversible. The void galaxy will exist in its own bubble of causality, completely disconnected from the rest of the universe. Even galaxies in denser regions will experience this future isolation, though on longer timescales. A galaxy in a rich cluster will remain gravitationally bound to that cluster, but the cluster itself will become isolated from other clusters. The distances between clusters will grow until neighbouring clusters recede beyond the horizon. 1 billion years from now, the night sky of a galaxy in a cluster will show fewer distant galaxies than it does today. 10 billion years from now, it will show even fewer. 100 billion years from now, the only galaxies visible will be those within the local cluster, gravitationally bound and unable to escape each other. Everything else will have receded beyond the horizon. The expansion will also affect the voids themselves in ways that go beyond simple growth. As the voids expand, the few galaxies within them will become even more isolated, and the gas and dark matter that remain will be stretched even thinner. The density within voids, already a small fraction of the cosmic average, will decrease further. The voids will become more and more empty until they are nearly indistinguishable from the vacuum of space itself. The difference between a void and the intergalactic medium outside voids will diminish, as both become increasingly sparse. The future separation is not uniform across the universe. Regions that are currently gravitationally bound will resist the expansion and remain coherent. Our local group, which includes the Milky Way and Andromeda, will eventually merge into a single large elliptical galaxy. This merger will occur in roughly 4 billion years, driven by the mutual gravitational attraction of the two galaxies. Once merged, the resulting galaxy will remain stable, held together by its own gravity despite the expansion of space around it. But beyond the local group, the expansion will dominate. The nearest galaxy cluster, the Virgo cluster, is currently about 50 million light-years away. Over time, it will recede farther and farther, eventually crossing the horizon and disappearing from view. This means that in the far future, an observer in our merged local group galaxy would see a universe very different from the one we see today. The night sky would contain only the stars of the merged galaxy and perhaps a few nearby dwarf galaxies that were also part of the local group. No other galaxies would be visible. The cosmic microwave background would still be present, though it would have cooled to an extremely low temperature due to the expansion. There would be no evidence of the cosmic web, no sign of the vast structures of filaments and voids that we map today. The universe would appear empty except for the single galaxy and its immediate companions. This future universe would resemble, in some ways, the universe as it appeared to astronomers in the early 20th century, before Edwin Hubble discovered that the universe was expanding and that the spiral nebulae were actually distant galaxies. Early astronomers believed the Milky Way was the entire universe, surrounded by empty space. In the far future, an astronomer in the merged local group galaxy might reach the same conclusion, not because they lack the technology to see farther, but because there is genuinely nothing else to see. The expansion will have carried everything else beyond the horizon. The voids in this future will have won. They will occupy nearly all of the universe's volume. The galaxies and clusters that we think of as the universe will be rare exceptions, tiny islands of matter in an ocean of expanding emptiness that stretches without limit. The foam structure of the cosmic web will have dissolved, leaving only isolated bubbles of matter separated by uncrossable distances. The universe will be dominated by absence, by the voids that were always the majority, but which will become even more so as the expansion continues. There is something deeply unsettling about this future. It suggests that the universe we observe today, with its rich structure of galaxies and filaments, its clusters and superclusters, its visible cosmic web, is a temporary condition. The structure exists now, but it will not last. The voids are expanding, the horizons are shrinking, and the connections between distant structures are breaking. The universe is fragmenting into isolated regions that will never interact again. The future is one of increasing isolation, increasing emptiness, and increasing darkness. This fragmentation is irreversible. The expansion driven by dark energy cannot be stopped or reversed, at least not according to our current understanding of physics. The voids will continue to grow. The horizons will continue to shrink. The universe will continue to pull apart, and in the end, each gravitationally bound structure, each galaxy cluster, each merged galaxy will exist alone, surrounded by an expanding void that grows without limit, unable to see or communicate with any other structure, isolated in its own bubble of space that expands faster than light can cross it. The future separation is not immediate. It will take tens or hundreds of billions of years for the full effects to become apparent, but the process has already begun. The voids are expanding now, the horizons are receding now, the universe is becoming more isolated and more fragmented with every passing moment. We are living in an era when the cosmic web is still visible, when galaxies are still close enough to interact, when the structure of the universe can still be mapped and understood. But this era will not last. It is a brief window in cosmic history, sandwiched between the early universe when structure was just forming, and the far future when structure will have dissolved into isolated fragments, separated by infinite voids. The voids are not just growing in size, they are growing in dominance. They are becoming the default state of the universe, the condition that defines almost all of space and almost all of time. The galaxies, the stars, the structures we observe, these are transient exceptions. The voids are the rule. They are the majority now, and they will be an even larger majority in the future. The universe is mostly voids, and it will become more so. The separation is inevitable, and it is accelerating. The future is not one of connection and interaction. It is one of isolation, fragmentation, and emptiness without end. A void is empty space. This is what the word means in ordinary language, and it is what the word means in cosmology. But understanding what empty space means at cosmic scale changes everything. It is not the absence of something that should be there. It is the natural state of the universe, the condition that occupies most of its volume and defines most of its structure. The voids are not failures. They are not gaps waiting to be filled. They are the architecture itself, the vast volumes around which the thin filaments of galaxies arrange themselves like surfaces on bubbles. We live in one of those thin surfaces surrounded by galaxies, looking out at a universe that appears full because we can see thousands of galaxies in every direction. But this appearance is misleading. Most of the universe is not like our neighborhood. Most of the universe is the voids. When you consider the true scale of these structures, the distances involved begin to exceed intuition. 100 million light-years across, 300 million light-years, nearly 1 billion light-years for the largest supervoids. Light itself, travelling at the maximum possible speed, requires hundreds of millions of years to cross these distances. During that crossing, entire evolutionary epochs pass. Stars are born and die, galaxies evolve and age. The universe itself changes measurably. The voids are not just large in space, they are large in time, separating structures not only by distance but by duration. The voids are also growing. The expansion of the universe, driven by dark energy, stretches space within the voids faster than gravity can pull it back together. What is already empty becomes emptier. What is already vast becomes vaster. In the far future, the voids will dominate even more of the universe's volume than they do today. The galaxies will recede beyond each other's horizons. The cosmic web will dissolve into isolated fragments. The universe will become a collection of islands separated by uncrossable oceans of expanding emptiness. This is not a distant abstraction. It is the future trajectory of the cosmos, already in motion, already observable in the acceleration of expansion and the growth of cosmic structure. The voids we map today are larger than they were 1 billion years ago, and they will be larger still 1 billion years from now. The process is gradual but relentless. The universe is separating, fragmenting, becoming lonelier with every passing moment. And yet, for now, we can still see the structure. We can map the filaments and the voids. We can trace the cosmic web across billions of light years. We can observe galaxies on the far sides of voids and study the cold spots they create in the microwave background. We live in an era when the universe's architecture is still visible, still coherent, still connected enough that light from distant structures can reach us and tell us what is out there. This will not always be true. The window is closing, not quickly, but inevitably. Billions of years from now, observers in isolated galaxies will look out and see almost nothing. The voids will have expanded until they encompass everything beyond the local gravitationally bound cluster. The night sky will be dark except for the stars of the local galaxy. There will be no evidence of the cosmic web, no sign of the vast structures we see today. The universe will appear empty because from that vantage point it will be. We are small. Our galaxy is one among hundreds of billions. Our position in the cosmic web is unremarkable, a modest filament on the edge of a supercluster, bordering a void. We are not at the centre of anything. We are not special in location or in scale, but we are here now, in this brief era when the universe's structure is visible, and when the voids, though vast and growing, have not yet consumed everything. The voids remind us that the universe is not designed for us or for anything. It is not optimized for visibility or for connection. It simply exists, structured by gravity and expansion, organized into a foam of emptiness and thin surfaces. We happen to live on one of those surfaces looking outward, capable of understanding what we see but incapable of changing it. The voids are the universe's dominant condition. The galaxies are the exception, and we, living in a galaxy among galaxies, are living in an exception to an exception, a rare and temporary configuration of matter and space that will not last. The universe is mostly empty. It always has been, and it always will be. The voids are not the problem, they are the answer. They are what the universe becomes when gravity and time and expansion are left to work across billions of years. They are the true scale, and understanding them means understanding that absence, at cosmic scale, is not the opposite of existence. It is existence itself, in its most common and most enduring form.